Good morning, everyone. And I'm Shuna Ni, and I'm currently an assistant professor in the Department of Fire Protection Engineering in the University of Maryland College Park. And this is just one slide to introduce myself. And my research is focused on probabilistic structure for engineering, fire-related multiple hazards, fire safety or mass timber building, and fire forensic. And also, I have a couple of projects focused on impacts of fire on civil infrastructure system. And recently, we also collaborate with the other faculty in computer science and EE to promote the smarter firefighting. And in today's topic, I would like to introduce one risk-based fire loss estimation framework we have developed. So first, I would like to introduce what is the structure fire protection and why is it important. So for a building, and when the building is in fire, and usually there's a lot of different measures to protect a building. For example, fire detection and alarm system, and fire suppression system, smoke and control system, and escape facilities. And structure fire protection is one of the fire protection measures. So the structure fire protection is to mitigate the risk of structural failure and of the building under the fire. And so for one thing, it provides structural integrity under fire to ensure that the life safety of occupants and the first responders. And for another thing, structure fire protection is to limit the structure fire damage to mitigate the social economic loss of when a building or the other type of structure was damaged to fire. So basically, in summary, and the structure fire protection have two main functions. One is to promote the life safety, and the other one is to help the function recovery of our building structures. So no matter for life safety or function recovery, it requires a framework for comprehensive assessing the fire risk to a structure. So which for one thing, it can help us to output the risk information at both the system and the component level. And for another thing, and this framework is supposed to include the uncertainties which come from the occurrence and growth of fire, as well as the structural response. So such type of framework, and it will provide a methodology for the risk-informed performance-based design for structure fire protection, and also its output will facilitate the analysis of structural recovery after a fire. So this similar framework already being developed in earthquake engineering, for earthquake engineering, and basically it follows a four-step hazard analysis, structure analysis, damage analysis, and loss analysis. So, but a similar framework is not exist for fire risk, fire hazard. So what we have done is we developed a framework. But there's a couple of challenges to develop such a framework for fire hazards. For one thing is that when fire happens, you never know where the fire begins. So there's some spatial uncertainties. Another thing is that the fire damage is very gradual level or repair efforts for non-collapse scenarios. It's easy to quantify the repair efforts for if a building is collapsed. But for reinforced concrete structure, usually those buildings have a relative good fire resistance. So under the fire hazard, this building usually does not collapse. So the damage is relative have a gradual levels of repair efforts for this type of non-collapse scenarios, and it's very difficult to quantify the repair efforts. Another thing is that for the building, when the building is under the fire, it's not in a lot of studies, they only study one component. For example, they study a column, this is a column and this is a beam. And so they usually just study the response of one column or one beam. But those are individual isolated structure components. But in reality, each structure component in a building, they interact with each other. So how to consider the interaction between each component, and which is very important. We have to consider the interaction of each component when we try to quantify the fire damage of a building in a fires. Another thing is that fire damage is a multiple physical damage. For one thing, due to the thermal heat transfer, the concrete, let's take the concrete building for example. The concrete will have some sporing damage, which is due to the thermal exposure. And also due to the thermal expansion, and also due to the degradation of the material property stress under the fire, and a lot of structure component will have a large deformation under the fire. So when we quantify the fire damage to a building, we have to consider both types of damage. One is from fire exposure, and due to the heat transfer, the other is because of the large deformation of the structure member under the fires. So this is a framework we have developed, and this have been published, already published in 2021. So basically, we follow the similar procedure as earthquake, because we have fire hazard analysis and fire thermomechanical analysis, damage analysis, and loss analysis. And this is a similar procedure like earthquake, but we consider the different scenarios in order to consider the spatial uncertainties. Since a fire happens, you never know where the fire begins. But when earthquake comes, and this building, the whole building is exposed to earthquake. It's not just one compartment or one room is exposed to earthquake, which is very different from fire. But fire is very possible. Just one room or one story is exposed to fire, rather than the whole building is exposed to fire. So in order to consider those spatial uncertainties, and we consider the different scenarios, and so basically this first step repeated for the different scenarios, and ultimately help us to estimate the fire losses. So the first part is in this framework is a fire hazard analysis. It mainly tries to identify the probability of a fire happens. So which is what is not my research focus, and which usually you can do using FDS to consider the uncertainty of fire load or ventilation condition, and ultimately you can figure out what's the fire the probability of a fire happens. So the second step is the fire thermomechanical analysis. It mainly to analyzing how the structure responds under the fire, but since it's a probabilistic framework, and everything has to be described in a probabilistic manner. So what we do is, and the main output of this step is to the probabilistic distribution of the engineering demand parameters. So the next step is the damage analysis. Once we know the probabilistic distribution of the engineering demand parameters, and we compare to the different definition of the different damage levels, and then we can, based on the fragility function, and we can analyzing the building's probability of collapse. And if the building does not collapse, and we can quantify the probability of each structural component in a building when it's in one specific damage. So we basically calculate the probability of structural component at each damage levels. So the last step is the loss analysis. So based on the probability of damage at each damage level and the probability of the structure collapse. And then we also consider the repair cost. And finally, definitely the repair cost is also described in a probabilistic manner. So finally, we can calculate the fire loss, and this fire loss, it can be in a probabilistic manner, but for this framework, we mainly estimate output the mean value, so expected value. So in the fire thermomechanical analysis, we develop a lot of methodology to simulate, to structure a building response under the fire. So since usually this is the majority part for structural engineering, analyzing how a building responds under the fire. But in reality, in the traditional method, when you're analyzing a building's response under the fire, we can using I define the fire load, and then I define the I analyzing how a building's how the file develop, and then those file load will input to the heat transfer analysis to analyzing how what's the temperature distribution in a structure component, and then we're analyzing a building's response under fire. So everything is in a deterministic manner, but in reality, uncertainty is exists everywhere, right? Even so, what in our methodology, and we rather do using a deterministic manner, we consider those uncertainties. We consider the uncertainty from opening factor, and we consider the uncertainty in mechanical loads, material property, and the other variables. So finally, what we use in the Monte Carlo analysis or the other methods, and we describe a building's response in a probabilistic manner. So rather than to tell people what's the deformation, it's 100 millimeter or not, we tell people, and the deformation of this slab under the fire is follow a log normal distribution, and the mean value is what, and the standard deviation is what. So this is what we have done. And in order to make this happen, so you have to quantify, in order to get the probabilistic distribution of the building response, and we need to quantify what's the probabilistic distribution of the opening factor, and what's the probabilistic distribution of the mechanical loads and material property and the other variable. And my research mainly to focus on the probabilistic of the material properties under the high temperature. This is some simulation methodology we have developed. So this is the probabilistic temperature-dependent concrete model we have developed. And basically, this model is this is all the test data we have collected. So as the temperature increase and the material strength will decrease for the concrete. And so the data, if you crack the data, and there's a lot of uncertainties. So we try to develop the probabilistic model to describe such uncertainties. So what we did is we're using the Wembu distribution to develop the probabilistic distribution of the concrete strength at each temperature. And then we can get the probabilistic Wembu distribution for the concrete strength at a different temperature, and then we fitted a function of the parameter for the Wembu distribution as our temperatures. So this is ultimately the probabilistic model we have developed, and from this plot we found that our model is able to describe the uncertainties of the material strength at high temperature. And this is the solid line is the mean value of this model, and the red dash line is the deterministic model from the yellow code. And basically our mean value is very close to the yellow code. Well, if you look at the 0.5 quintile and the 0.05 quintile and 0.95 quintile of this probabilistic model, and basically it covers the range of the material strength at each temperature. So this model is already been incorporated in the a software which is called Sophia, and which is a very specific software for structural engineering. And besides this concrete model, we also developed the model for the steel model. So our next step is to develop a similar model for the other type of construction material. For example, the timber. Timber is our next target. So once you analyzing the building's response in a probabilistic manner in this step, and you output the probabilistic distribution of the engineering demand parameters, and the next step is the damage analysis. I know my structural response, and I know it's in a probabilistic manner. So then I analyzing what's the probability of the building collapse, and what's the damage, the probability for each structure component at each damage level if the building is not collapsed. So basically, what type of damage we have considered in the framework? And we consider the two scenarios, collapse and non-collapse. If the building does not collapse and we consider the fire damage in fire region and also the non-fire regions. So basically, if the fire happens in these areas, and those rooms will be exposed to fire directly, but the other part is non-fire regions. But the non-fire region, it does not mean it does not have fire damage. So when the building under fire, for example, this is a floor system. When the floor system is under fire, and it will expand due to the thermal expansion. And those thermal expansions, since each structure component is connected to each other. So each structure component is connected to each other. So when the slab expanded, and which also will leading some deformation in the other structure component, ultimately leading to some cracking or the other type of either the damage to the structure component or the non-structure component. And so in the damage analysis, as I have mentioned, it's mainly to analyzing if building the collapse and what we want to do, the probability of building collapse. And also for the non-collapse scenarios, we need to identify the probability of a component at a specific damage state. And this part is involve a lot of calculation. You need to define the fragility function, and you need to calculate the probability. And how to define the fragility function for the fire damage, it's different from earthquake. And earthquake, there's a lot of test data, and you can define those fragility function based on those test data for different type of structure component. While for the fire damage, for the fire structural response under the fire, the test data is relatively limited. So what we did is mainly to based on the numerical data. Here, I don't want to explain too much since there's too much equation. So here, just some general idea. This part, the majority work, it defines the fragility function. Also, ultimately, once you get the fragility function, and you can calculate the probability or component at a specific damage state. And this part is easy. Basically, you running using Monte Carlo analysis, and then you counter how many scenarios collapse and how many scenarios is uncollapsed, and then the number of collapse scenario divided by the total number is the probability of building collapse. The difficult part is in this part, and the reason it's difficult is mainly because you have to figure out the fragility function first. So for this part, if you are interested, you can refer my paper, which we have very whole section to describe our idea how to define those fragility functions. So for the fire damage, another difficult part is, as I have mentioned, it's multiple physical problems. So basically, the structure component, it will have deformation. For example, the deflection of the floor system, and also will be have subsporing due to the heat transfer. And this is a test which I done many years ago, and it's a whole building full-scale fire tester. And even though this part is not exposed to fire directly, and due to the deformation of the slab, and this ultimately this connection fails. And this is because each structure component is connected to each other, even though they are not exposed to fire, but its surrounding structure component is have large deformation, ultimately leading to the failure of this connection. So basically, the deformation, the damage need have two types. One is the section damage due to heat penetration. Concrete sporing is one example. Another is because the residual deformation. After the fire, even the temperature is cooling down, and the large deformation cannot recover completely. So this residual deformation also need to be quantified when we to estimate the fire damage to a building. So in the engineering demand parameters, when we have to different from earthquake. For earthquake, you can just define, I can assume the deformation, the interstory drift is the engineering demand parameter. But for fire hazard, building's response under fire, we have to define two sets of engineering demand parameter. One is to represent the section damage due to heat penetration, and the other set of engineering demand parameter represents residual deformations. So this is also another different part from our framework data, which is different from the earthquake, the performance earthquake-based earthquake engineering framework. So ultimately, when you define the fragility function, you define the engineering. In reality, engineering demand parameter you have to define in this step. And this step is mainly to define the fragility function to calculate the different type of probabilities. So now you have the the probability of each structure component at each damage level, and then in the loss analysis, you need to quantify the repair cost for each type of each damage levels, and then to calculate the total cost. So in the loss analysis, and what we need to do is that we need to define the total replace cost of a building. If a building is collapsed, and the fire cost will be the total replace cost. So and the FEMA, here we have referred some study by earthquake peoples. So we assume the replace cost for the content in a building is equal to the total replace cost of the building. So when you define the total replace cost, it's not just the structure and non-structure component for a building, and when it's damaged or fire, the content is also a big loss. And this even is equal to the total cost of the building. It basically the total cost of the structure and non-structure component of a building. So the content loss is that you have to consider when you estimate the fire loss to a building. And the fire damage to content, sometimes it's not just come from the direct exposure to fire, and sometimes it's because of firefighting, and there's also water will damage content. And the smoke deposit, the smoke, even it's not it burned, even a furniture is not burned by fire, but the smoke will deposit on the surface, and which will also will leading to the damage of the content. So for when we estimate the repair cost for each damage level, and first we need to identify the repair action. We define the different damage level from damage 1 to damage 4. But when you estimate the loss, you have to know first how I repair those damage. And since how I repair mainly determined how much I need to pay for this repair. So first you need to identify the repair action, and then to estimate the main repair cost. And those data this is a couple of construction cost data which you can use to help you to estimate. And how to identify the repair action, you have to talking to those engineer people, engineers in different construction design company, and and to get talking with them to know how they repair that, and then to estimate the cost of each repair effort. So with this, and then we also make sure, since everything is uncertainty, right? So even the repair cost is not a deterministic value, and we also need to consider there's some uncertainties in the repair cost, and because the different company will have provide a different quota, and they have different budget for the same damage. So what we did is we also assume the repair cost follow on log-normal distribution, and this how. This is referred to some study by earthquake people. They already they did some survey and found that even the repair cost is follows the log-normal distribution. So after you have defined all these costs and also describe those costs as a log-normal distribution, and then we can estimate the total cost. And there, in the following is just a basic calculations. So this is the whole framework, and we also have applied this framework to our case study. And this is our 5-story reinforced concrete building, and what was the damage we consider is structure component damage, non-structure component damage, and the content. And also we have estimated the cost, and we consider the replace cost according to the famous numbers, and we estimate the repair cost and for each structure component according to the data provided by IS mean data set. And this is a very this is a construction cost data, which you have a manual. You can refer to the manual, or they also help provide online data sets. And also, we assume the replace cost for the content in the building is the total replace cost of the building, which including the building's cost for structure component and the non-structural component. So this is what we did. We consider 3 different scenarios. For the first scenario, we consider the fire is only in a 7 meter by 7 meter compartment, but we consider the here we just do not just estimate the fire loss at this compartment. This is just an example, and we assume the fire is confined in a 7 meter by 7 meter compartment, but we consider the uncertainty in locations. So basically, we consider the fire in each of these component in each of these compartment and in each different stories. So ultimately, this is the total fire loss we have estimated. And we found that the content in reality is up to 50%. It is a bigger loss for a building if a building is damaged by fire, and the non-structural component and also have a lot of loss, while the structural component, although my research focused on the structural fire damage, in reality, the fire damage loss due to structure is relatively limited. For one thing is because this is what we analyze is a reinforced concrete structure is relative fire resistance, and if we study steel structure or mass timber structure, possibly it will be a different scenarios. Since the steel structure and mass timber structure is more vulnerable, it's more easily to be damaged by the fires. And also we have considered another scenarios, and which is the case 2 is we assume all the fire is confined in 21 meter by 21 meter, but we consider its potential different locations in our building. And the total cost is it's almost 8 times the first scenarios. So which means that if a fire is confined well, if we can confine the fire just in one compartment and prevent it to spread to the other areas, and in reality we can reduce the fire loss significantly. And also we're using the event tree, something similar to the event tree, to analyze, combine those scenarios. Assume the fire it started in a 7 meter by 7 meter compartment first, and then it has a probability of 5% to spread to a region of 21 meter by 21 meters. And we're using those event tree and ultimately to estimate such a scenarios. And the total cost is compared to the first scenario, it increased by 28%. So in case 1 and case 2, we assume the fire is just confined to a 7 meter by 7 meter compartment or 21 meter by 21 meter compartment. In reality, the fire it will spread, right? So it have, but here we assume the probability of the spread is have 5%. This is a very rough estimation, and then we consider, so if such a scenarios and for the fire began in 7 meter by 7 meter compartment have such a probability to spread to a large area, what's the fire loss? So compared to the first case 1, the total fire loss increased by 28%. So which also tell us confining a fire is very important to reduce the fire loss. That's why in the structure design or in the fire safety design, there's a lot of firewalls. And those firewalls is trying to make sure when the fire happens in one area of the building, those firewall can prevent the fire to spread to the other side of the building. And this firewall, and also there's a fire resistant floor system, and those floor system is trying to make sure the fire happens in one story and it does not spread to the other stories. So here's some conclusion. So both the life safety and function require a comprehensive framework for estimating the fire risk to a building's structure. So what we did is we developed a frame. For one thing, such type of framework, for one thing is for provide approach for risk-informed performance-based design or building structural fire protection, and also it will facilitate the analysis of buildings recovery after the fire. So for this point, because we already analyzing, our framework can provide the information of the probability of buildings collapse, or if the building does not collapse, and we can estimate the probability of structure component at each damage level. So this information will become the input for the following study, if we want to analyze it. So how long takes the building to recover to its normal condition? So when we to estimate the recovery, we have to first know what's its damage level first. So this is what this term means. And also the PEER methodology for earthquake was adapted with the fire-specific variables for fire hazards. So basically, our framework is based on the framework for earthquake engineering. And we consider the interaction between each structure component in our building. And we develop a probabilistic material model for high temperature. And we define a dual set of engineering bound parameters to capture the multiple physical nature of the fire damage. And also we define the fragility and loss function based on the literature data for post-fire scenarios, repairs, and also based on some numerical analysis. And we also have 3 case studies for AC building, and we consider here we only consider direct fire loss due to the structure damage. In reality, the direct fire loss due to structure damage is very limited. And the most loss is come from the content and the non-structural fire damage, the fire damage to the non-structural component. And also and the fire spread another conclusion is the fire spread will increase the fire damage loss significantly. So it's very important to confine the fire in one compartment. And here I would like to show you some of my current research, just a quicker overview. And so nowadays, the mass timber building has been, the timber strong building, mass timber building is already in United States, the codes already around to 18 stories. So because the mass timber have a very good economical and sustainability benefits. But one thing, it reduces compared to the manufacturing of the traditional construction materials. The manufacturing process of mass timber products emit less carbons, and also the structure itself can store the carbons, right? So that's why nowadays there's a lot of tall mass timber building has been proposed or constructed all over the world. So while the problem is that the mass timber itself is a combustible material, which means the construction material itself is combustible, right? So which means we have to have much higher requirements on its fire safeties. So here's those in the past decades, there's a lot of fire tests have been done on the mass timber compartment. So basically, those buildings are constructed by mass timber. It's different from the light frame constructions, and which those mass timber structure compartment is relative to the structure component have a large dimensions. So what they have found is that they found that the mass timber, the construction itself, since the building itself is constructed by those combustible material mass timber products, and those mass timber products is also will burning under the fire, and which will impact the fire dynamics in those compartments significantly. So which means the building itself is burning. It's very different from traditional building. So which also means the current a lot of fire model, combustion model, fire dynamics model, they are designed or they are proposed for those non-structure components, non-structure, non-combustible buildings, right? So which means the current methodology does not work. So what we have did, we proposed some combustion model for ventilation control fire in CLT compartment. CLT is cross-laminated timber. It's one type of mass timber products. So how to consider the impact of those burning of those mass timber itself when we define the combustion model for a mass timber compartment. How to consider the impact of the construction material itself in the fire dynamics in a compartment. This is the model we have developed and it's already published. And we validated this model, and we found that those are some validation results. I cannot say it's a perfect model. Definitely, there's a lot of work need to be done further. But at least, for some tester, it can well simulate the combustion or the fire dynamics, the compartment of fire dynamics. Those are all some validation, and so this is one major research topic I'm working on in the past 2 years. And also, I did some research about fire forensics. So fire forensics is mainly to identify where the fire begins in a compartment. So what we did, we tried to, in the traditionally, the fire investigation is really very rely on people's visual observation and judgment. So if a very experienced fire investigator, his conclusion possibly will be very different from a new fire investigators. And I also get the certificate to be a fire investigator. But for me, if I go to a fire site, my conclusion possibly will be very different from those people already working in this field for a couple of years. Which means this process, the fire investigation process, it's still very subjectively. And they describe a lot of things very qualitatively rather quantitatively. What my work did, what we did is develop some data-driven tools to quantify, to make the fire investigation process more quantitatively and objectively, and does not rely on human beings' visual observation and judgment. So this is one model we have. This is one of the model we have developed. We developed a data-driven model to predicting the degree of fire damage. So basically, after the fire, those gypsum boards in a compartment will be have damage. And also we call it the fire effect. So a group of fire effect, we call it fire pattern. So this fire pattern is very important information for people to identify where the fire begins and what caused the fire. So in doing the fire investigation, we have to identify the relative different damage level of those fire patterns at different areas. For example, here definitely have less fire damage, right? And here have relative more significant fire damage. For this plot, it's easy to identify the different levels. But for a lot of scenarios, it's very difficult to quantify which area have more large fire damage and which area have less fire damage. So in the traditional methods, people based on the visual observation and identity, no, this is much more significant than this. But for this picture, possibly this method definitely work, but there's a lot of fire incidents, and the relative damage level between different areas is very difficult distinguishing. So what we did is, and we label, we test, we do a lot of fire tests, and we collect the image data, and we label the different damage levels. This is damage level 5, and this is damage 0, and we collect a lot of data. And then we develop a data-driven model, and based on those image analysis and those data-driven model can tell people directly what's the damage level. And this is damage level, let's assume it's damage level 3, and this damage 0, no damage. So this is the methodology we have used. And this data-driven model is based on a bag of visual words classification scheme, and we training the classification model using support vector machines. And basically, here's some results. So basically, the model is if we just identify each sub-image, and our model it have very high accuracy, 98.9%, and basically it can be, and what is the damage level given by the model is almost very accurate, and compared to the manual classification. And also this plot is just if we tested almost 200 images or those sub images, small images to identify its damage level, and the accuracy is very high. And also we have using this model to some entire image and to estimate the average fire damage level for our gypsum boards, and the accuracy reduced a little bit, not only some kind of reduce, and so the manual difference between the manual classification and the algorithm classification is 19.8%, And one reason is because our model is based to treat, since there's a lot of, if you look at a lot of sub-images, they are not just have one damage level, especially this one. Some image have multiple different damage levels, and our model is very good to identify if a sub image only have one damage level. So that's why when you use the tool for those entire image, and for some image it have a multiple damage level, and the accuracy will reduce. And we are still working on try to collect more data and more high quality data, and to increase our training data sets, and also would like to see how to make sure this model can also have very high accuracy when they to estimate the damage level for those sub images which have multiple damage levels. Thank you so much. Yes, that's all.